Hi everyone, today we're going to have a look at a probability review. So to start off with things, we're going to look at something relatively simple, and that is a spinner with numbers 1 to 8. And so I've drawn a diagram up the top here as shown, and we've got numbers 1 to 8, and I'm going to spin it, and I'm interested in finding the probabilities of different events. So to start with, I might be interested in finding the probability that it lands on a 1. And to do that, I work out the number of um, countable um, outcomes. So the number of outcomes I could achieve is numbers 1 to 8. So there's 8 possibilities that I could get. 1, 2, 3, all the way up to 8. And this on the top is going to be the number that I am interested in. So after a 1, how many 1s can I get? Well, there's only one. There's only one way I can get a 1. So my probability of getting a 1 from this spinner would be 1/8. Another one I could be interested is an even number. So again, the number I'm interested in over the number of countable outcomes in total. So same spinner, there's 8 counted, or there's 8 possible outcomes in total, and I'm after an even number. Well, that could be a 2, a 4, a 6, or an 8. So there's 4. So I have 4 over 8. I can leave it like that or simplify as a half. So that's essentially a summary of or a bit of a recap on probability that we would have encountered before. For any event, we'll say A. So my event A, this could be um, the event of spinning the spinner. Um, I have a probability of A. Has to be between 0 and 1. So there's either a 0% chance that the event A happens or occurs, or there's a 100% chance that it occurs, and it's between 0 and 1, so it's usually a decimal, as we can see here, zero point 0.8 as or a half as 0.5. So either way, um, it's usually a decimal for our probabilities. If we had the probability of A is equal to 0, there is no chance that that would happen. So for example, for this one, what's the probability that I get a 9? Well, there's no 9s in my spinner out of 8 possible outcomes, so it's just 0. Whereas if I was looking at the probability of A and I find that it's equal to 1, there is a certain chance that I will get that event. So what's the probability I get any number between 1 and 8? Well, I can get 1, 2, 3, all the way up to 8 out of 8 possible outcomes. So I will definitely get one number out of 8 for that event. Complementary events is another interesting concept. So complementary events. So I could be looking at finding the probability of getting um, a 2. Well, I can find that that is going to be the same as finding a certain chance minus the probability of 1, 3, 4, all the way up to 8. So every other number except for 2. Um, so every other number would be there's 7 other numbers other than 2 out of 8. So the probability of 2 would be 1/8. Um, so the probability of let's say event M in this case, something different. 1 take the probability of M. So M dash means not M. So we're saying the probability of not M. So the probability of getting sorry, other way around. Not M. So this is just probability of 2 is equal to 1 minus the probability of not getting 2. Okay, so that's complementary events. Okay, so we've got a bit of an example. So this is example 1. We've got a spinning wheel split up into 8 equal parts. So like before, we've got a spinner with 8 equal parts, numbered 1 to 8. Except this time we've got a biased wheel, so the wheel is biased, such that we've got the probability of obtaining an 8 is 0.3. So it's a little bit higher than any other outcome. And what we want to work out is calculating the probability that we actually get a 4. So this is what we want. What is that probability? So I can use a complementary event. So the probability of getting not an 8, so not an 8, is going to be 1 minus the probability of actually getting the 8. So 1 minus the probability of 8 is 0.3. So the probability of getting any other number except for 8 is 0.7. Which makes sense because 0.3 plus all these other numbers will give me 1 in total. So it's the difference between them. So now, every other number that I've got left over is 0.7. And all these numbers are equal probable, so it's equal chance of getting these other numbers. So the probability of getting a 4 is going to be 0.7, and I'm going to divide it up into 7 bits. Because there's 7 left over. So to work that out, 0.7 divided by 7, which gives me 0.1. Now, if A is the event that the number obtained is even, so let's say the event A is even, when I calculate the probability of A and not A, or A dash. So A is even, that means that we're looking at the numbers 2, 3, 2, 4. So 2, 4, 6, or 8. So probability of A is going to be finding the probability of getting a probability of getting a 2 plus the probability of getting a 4 plus probability of 6 and the probability of an 8. Now we worked out the probability of getting a 4 was 0.1. Now that's the same as a 1, a 2, a 3, a 4, a 5, or a 6, and 7. So the probability of 2 is 0.1, 0.1, and 0.1. Except for probability of 8, we know is 0.3. And so if we add them all up, we get 0.6. So there's a 0.6 chance of getting the event A, which is an even number. Which means that there's a 0.4 chance of getting not A. And that comes from this complementary formula. So the probability of not A is equal to 1 minus the probability that we do have A. So 1 takes 0.6, which is 0.4. So 0.4 chance of getting not A, or in other words, getting an odd number. So now we're going to have a look at Venn diagrams. So same example, I've got the spinor counter from 1 to 8, and my event A is all even numbers, and event B is going to be the prime numbers on that spinny circle. So Venn diagrams, essentially two circles usually connected together, surrounded by a box. And we label each circle as either A or B, or depending on what our events are. So in the middle, where they intersect, is the intersection. So it's A and B. So this little N is the intersection, or in other words, we can think of it as A and B. The other one, which is a little bit harder to picture, is A or B, this little U for union, and we think of it as or, so A or B, so A or B. Anyway, we'll have a look at this. So this is usually the first bit that we want to work out from our information. So what occurs in both A and B? So A is even numbers from 1 to 8. So let's say A is 2, 4, 6, and 8. Whereas B is the prime numbers. So 1, 2, 3, 5, and 7. So when I'm working out A and B, we need to work out these numbers that are in both of them. So it's just 2 in this case. So I would have number 2 in there, which means I've got 4, 6, and 8 left over in the other bit of A, and 1, 3, 5, and 7 in B. So this whole circle is event A, this whole circle is event B, but when I'm looking at just this part here, not including the 2, that would be A and not B. Okay, because 2 is actually in B, so it's not B. It's everything outside of B. And over here, is everything but A. So it's not A and B. And then on the outside, not colouring in any of the circles, is not A and not B. And A or B, a little bit harder to describe, but it's just the numbers that occur in either A or B. So A or B would be the numbers 1, 2, 3, 4, 5, 6, and 7 plus 8. So A or B is the numbers that occur in either A or B. So that's a bit of a recap on Venn diagrams. And from here, we can have a look at what's called the addition formula. So the addition formula is quite useful. I won't go through how we come up with it, but it's finding the probability A or B, A union B, is the same as finding the probability of A plus the probability of B minus the probability of A and B. So just a formula that we can use to work out probabilities. Okay, so just a quick example of using Venn diagrams. So we've got the situation where we've surveyed 50 shoppers, and we find that 25 of those shoppers bought apples during that supermarket, and 30 of them bought chocolate. 20 people bought both apples and chocolate. So drawing a Venn diagram, and we've got the either event A or C. And we need to work out what numbers go where. Now to start with, we usually want to work out what this number in here is. And that's where both A and C occur. So how many people bought both apples and chocolate? Well, there was 20. So we'd put 20 in there. Which means for event A, we had 25 people buying apples. We've already got 20, which means there's 5 left over. And then for C, we had 30 people buying chocolate. Well, we already have 20, so there's 10 left over. If we add that up, 20 plus 10 plus 5 will give us 35 people buying either apples or chocolates. But we have 50 people in total that we've surveyed. So that means that there's 50 minus 35 gives us 15 people who buy neither apples or chocolate. So that's a probability, a Venn diagram of our situation. So if we were looking at finding the probability that we have apples, someone buys an apple, well, there's 20 plus 5, so 25 people out of 50. So 25 out of 50. But we might be looking at the probability of A, but not C. So A, but not C. So it's this number in here because I'm not interested in these 20 people who did buy chocolates as well. So it's 5 out of 50. The probability of A and B, or C, sorry, would be the number in here, which is 20 out of 50. So it's just identifying what number we're actually interested in. The probability of neither A or C, well, it would be this 15 because we don't want A's, apples or chocolate. So 15 out of 15, 50, sorry. So that's using Venn diagrams. Another useful tool for probabilities is looking at probability tables, also known as Karnaugh maps. And it looks something like this. So we've got event A and not A, event B and not B. So this example, we've got finding the probability of A is 0.4, the probability of B is 0.7, and A and B is 0.2. And I want to put this information in a Karnaugh map. So just looking at the intersections of them, A and B, well, this is probability of A and B because it intersects both A and B. So for this case, we've got A and B is 0.2. For this bit in here, we've got the probability of not A and the probability of B. So not A, so not A, and the probability of B, which we'll work out in a moment. Here we've got the probability of A and the probability of not B. Again, we'll have a look at what that is in a moment because we can't easily identify it straight away. And then we've got probability of not A, probability of not B. Not A and the probability not B. Over here is going to be the probability of just A because we're looking at A and B plus not B. So if you think about our Venn diagram, here's A, here's B. A and B is this bit in here, A and B, plus not B is going to be this area in here, A and not B, which gives us the probability of A. And then similarly for down here, the probability of B and A, B and not A. So that's just the probability of B. So those two we can put into, so A is 0.4 and B is 0.7. So each row and column has to add up to these bits here, and overall the rows or the columns have to add up to 1. So 0.4 plus something has to be 1, 0.7 plus something has to be 1. So let's do those to start with. 0.4 and 0.6 give me 1. 0.7 and 0.3 gives me 1. And columns have to add up to the total down the bottom. So 0.2 plus something gives me 0.7. So the difference I have to add is 0.5. And then going across, 0.5 plus something gives me 0.6, which is 0.1. And I can go either across or down. We get 0.2 in either case. So there we go, mostly filled out. I just didn't write this bit here. So this is the probability of not B. This is the probability of not A. So that's quick and easy way to work out some things that aren't quite so easily to see from the original information. So all these values here. So Karnaugh map's quite useful for that reason alone. The last thing we're going to have a look at is tree diagrams and lattice diagrams. So we've got an example. We've got a four-sided dice. So it has 1, 2, 3, or 4 as its numbers. And we've got a coin getting tossed at the same time. So either heads or tails. So I want to draw what's called a lattice diagram. And essentially, on the it's basically a graph. We've got a coin, either heads or tails, and then we've got the die 1, 2, 3, or 4. And in the middle, we basically just put um, a little dot where it intersects. So we've got 8 possible outcomes, either a 1 and a tail, a 2 and a tail, 3 and a tail, etc., or 1 and a head, 2 and a head, 3 and a head, etc. So that's a lattice diagram. Essentially just labels how many outcomes we've got. So if I want to find out what the probability of getting a 1 and a tail on the dice, so a 1 on the dice and a tails on the coin, I can use the lattice diagram because there's only one way I can do that, which is over here, a 1 and a T. So there's 1 out of 1 to 8 different possible outcomes. So quite useful in that regards. The probability of the event of obtaining a number which is at least 3. Together with a head. Probability of at least a 3 and a head. So at least a 3 would be these ones here, except I want it a 3 and a head, so it's where they both occur. So there's 2 different ways I can get that. So quarter. Just to draw out a tree diagram, so um, that's using a lattice diagram. I might be interested in what a tree diagram looks like. So essentially, we have either a heads or a tails. So that's for the coin. And depending on what I get for the coin, depends, well, I'm either going to get a different number for okay, so there's my coin, heads or tails, and then the die. I then roll 1, 2, 3, or 4. So 1, 2, 3, and 4. So that would be a tree diagram. So um, looking at the probability of 1 and a tail. So head or tail was 0.5. There's a 50% chance on each, and each of the dice rolls is what's that? We'll just say 0.25, sorry, quarter. So there's four possible outcomes for each, so 0.25. So 1 and a tail, so tail and then a 1, it would be 0.5 times 0.25, which gives me the same answer, 1 over 8. And then same thing for at least a 3 and a head. Well, at least a 3 and a head, it's these two here, which you would get. Okay, either 1/8 that way or 1/8 that way, add them together, we get the same answer, which is 1 out of 4. So that's a probability review. So that's 8.2, and the next section we'll have a look at a bit more information. Thanks for watching.